sklearn, manifold, locally linear embedding. Description: Locally linear embedding (LLE) is a nonlinear dimensionality reduction technique that seeks to preserve local neighborhood relationships in the lower dimensional space. It assumes that each data point can be linearly reconstructed from its neighbors, and aims to find a low-dimensional representation that maintains these local relationships. Inputs: X. The input data, typically a 2D array of shape n samples. N features. Each row represents a data point in the high-dimensional space. N components, the desired number of dimensions in the lower dimensional embedding. This determines the dimensionality of the output. Outputs: Y. The reduced data, a 2D array of shape n samples. N components. Each row represents a data point in the lower dimensional space. Reconstruction error: the reconstruction error for each data point, which represents the deviation from the original data after projecting to the lower dimensional space. This can be used to evaluate the quality of the embedding. Steps: Neighborhood search: the algorithm first finds the k nearest neighbors for each data point in k high-dimensional space. This defines the local neighborhood structure. Weight calculation: based on the identified neighbors, weights are calculated for each data point to represent the contribution of its neighbors in reconstructing itself. This is done using a linear reconstruction approach. Embedding optimization: the algorithm then finds a lower dimensional representation of the data that minimizes the reconstruction error while preserving the local neighborhood relationships as defined by the weights. This is typically done using an optimization algorithm, such as eigen decomposition. Metrics: reconstruction error measures the average deviation of the original data from the reconstructed data in the lower dimensional space. A lower error indicates a better embedding. Neighborhood preservation measures how well the local neighborhood relationships are preserved in the lower dimensional space. This can be assessed using metrics like the preservation of distances between neighboring points. Visualization plots: scatter plot: the reduced data can be visualized in a scatter plot to explore the relationships between data points in the lower dimensional space. Pair plot: for lower dimensional embeddings, e.g., 2D or 3D. A pair plot can be used to visualize pairwise relationships between different components of K embedding. Fine-tune parameters: n neighbors, number of neighbors to consider for each data point. This influences the local neighborhood structure and the resulting embedding. Method: the method used to solve the optimization problem for finding the embedding. Common options include standard eigenvalue decomposition and modified using the Hessian of the cost function. Eigensolver: the eigenvalue decomposition method used to find the embedding. Options include auto, dense, RPAC, and log-PCG. Uncertainty methods: out-of-sample extension: while LLE is primarily designed for dimensionality reduction on training data, there are approaches for out-of-sample extension to project new data points to the learned embedding. This involves finding the nearest neighbors of the new point in the original high-dimensional space, and using the learned weights to project it to the lower dimensional space. Confidence intervals: estimating the uncertainty in the embedding can be done by analyzing K reconstruction error and its distribution. This can provide confidence intervals around the projected data points. Challenges and fixes. Challenge 1: high sensitivity to noise. LLE can be sensitive to noise in the input data, which can lead to inaccurate reconstruction and poor embeddings. Sample use case that resulted in challenge 1: a dataset with a high level of random noise might result in LLE misinterpreting noisy features is important for local neighborhood reconstruction. leading to a distorted embedding. Fixes to challenge 1. Preprocessing, applying noise reduction techniques such as smoothing or filtering to the input data before applying LLE. Robust weighing, using more robust methods for calculating weights that are less sensitive to outliers or noisy data points. Regularization, adding regularization terms to the optimization problem to penalize large weights or high reconstruction errors, which can help mitigate the impact of noise. Challenge 2. Computational complexity. LLE can be computationally expensive, particularly for large datasets with high dimensionality. Sample use case that resulted in challenge 2: analyzing a dataset with millions of data points and thousands of features might lead to long computation times for LLE. Fixes to challenge 2. Dimensionality reduction, applying a preliminary dimensionality reduction step using techniques like PCA to reduce the number of features before applying LLE. Random subsampling, using a random subsample of the data to train LLE, which can significantly reduce computation time while still providing a reasonable embedding. Approximate neighborhood search, employing efficient approximate nearest neighbor search algorithms to speed up the neighborhood search step. Optimized solver, choosing an efficient solver for the optimization problem, such as RPAC or LOB-PCG for larger datasets.